All right, so thank you very much for braving the weather and coming for this early morning talk. This is actually my first time being able to come, even though I'm local, just for personal reasons. But I'm very happy to be here. The motivation for a lot of this is on the arithmetic side of arithmetic quantum field theory. And so, in particular, for the entirety of the talk, I'll let F be a local or global field. I don't care about the characteristic, but I tend to think about things in characteristic zero. So F would be like a numbered field. And so one of the themes that I'd like to sort of emphasize today is that some of the structural ideas from this concept of relative Langlands duality in this recent work of David Ben-Zvi, Sakellaridis, and Venkatesh plays sort of a structural role in the arithmetic theory of periods. In particular, this sort of comes up in my work of endoscopy. So my outline for today is to try and discuss that connection, which goes through some basic questions that arise in just rationality results in the arithmetic setting, and then after I've explained that connection, go towards the applications to endoscopy. So with that being said, let me briefly say what I think of when I say relative Langlands. So I'll let G be a reductive group over my field F. And so to this, I can associate this Langlands dual group, G check, which I'll just always assume implicitly. I take over the complex numbers. And one of the things that's going to come up later is, it's important that because G arises as a group over this field F, I get an action of the Galois group of F on this complex reductive group, and so I get to form the Langlands L group. And the basic principle of that guides much of the Langlands program is that of functoriality. Namely, if I'm given two such things, so say I have a reductive group H and a map its L group to the reductive group, or to the L group of G, then that should correspond to some sort of transfer of representation theoretic objects on H to representation theoretic objects on G. So if F is local, we would think of taking representations of H of F to representations of G of F, and if F is global, attach the word automorphic to everything and think about representations of the adelic groups. Okay, and so just to briefly touch on the theme of endoscopy, some basic examples of such maps. For the majority of the talk, there's going to be little details about precisely whether or not it's an L group or not that I'm just going to completely ignore that come up throughout the theory of endoscopy. So I'll be aligning a lot of details like that. But the basic examples. Well, the first one is if H is trivial. Then this gives rise to the other sort of philosophical goal of Langlands, which will be useful to sort of formulate relative Langlands, namely reciprocity. So that if H is trivial, then this sort of a product is just a statement that if I have a map of the Galois group to L group, then that should correspond to a parameterization of these representations of G. And so that's an important principle that's related to this, and in fact makes the whole general principle of functoriality a little bit more easy to see. And so, I'm again, the idea that this should actually be the Galois group versus something more general like the Bay group, L group, these are sort of, I wanted to think in this talk, or these are sort of details that aren't too important. The other basic example is when I take a centralizer. So I'll take S to be a semi-simple element in this complex group, and then I take H to be centralizer inside of S. And maybe I want to assume some properties of how S interacts with the Galois action. But with this setup, this is the concept of endoscopic transfer. This so H gives rise to a quasi-split group H over F, and the transfer from this sort of an H that arises in this way. So if you take a centralizer, you want to take a connected component. This is called an endoscopic group. And the corresponding functorial transfer in this setting is the context of endoscopic transfer. And one of the reasons why this is most important is that this case plays an important role in understanding the fibers of these maps, so the notion of L packets. But from most of my motivation, when F is global, the context, the endoscopic groups play an important role as to these fundamental so-called stabilization of the Arthur-Selberg trace formula for G. So one of the things I would like to not do is assume that people think about trace formulas. The main takeaway from this, because it's going to show up in the relative setting in a minute, is that we would like to study representations, automorphic representations of G by maybe studying sort of invariant distributions associated to G. So this is some context of what's called a trace formula. It somehow encodes the traces of these representations. But this sort of a distribution is somehow, this is G of F invariant. But for various reasons related to functoriality, that's somehow insufficient to try and establish these sorts of transfers of representations. What is required to relate automorphic representations of H to representations of G are so-called geometrically invariant objects. And so what the stabilization does is it expresses the trace formula as a sum of things called stable trace formulas. So what they are is not really important. The point is that these are associated to these endoscopic groups H mod some notion of conjugacy. And so you somehow express this trace formula in terms of these more refined, these are called geometrically invariant. So these distributions would satisfy some stronger notion of invariance, and these are well equipped to study functoriality. So that's sort of the motivation for focusing on this particular case. Okay. All right, so that's sort of the background there. What about the context of relative Langlands? Well, I want to front load the perspective forward by Ben-Zvi, Sakellaridis, and Venkatesh, namely that one should extend this duality of groups G to G check. So Ben-Zvi, Sakellaridis, and Venkatesh extend the duality groups to a conjectural duality where you take G and a G variety and associate with dually, you'll have a G check, the group G check and a G check variety. So more specifically, they focus on Hamiltonian G varieties or G spaces that satisfy several conditions. And so M check will be something analogous. but now it's a variety of the dual group. And so this is the context that they would like to propose as a general, an extension of the duality of G and G check. And how does this relate to this more arithmetic setting? So, at least from the point of view that I've studied in the past, arithmetic point of view, the varieties that most often come up, certainly are not all of them, but what we begin with is we start with our group G and a nice subgroup of G. And to this, we associate the corresponding homogeneous space, G mod H. And typically we would make some assumption on what groups H we're interested in, so that this is a so-called, this is a spherical variety. So this is some condition. And then what is this Hamiltonian space? The M that you're interested in is the cotangent bundle of your variety. So that would be sort of the input that shows up in this context. But what is the arithmetic picture here? Well, arithmetically, or let me say representation theoretically, we're interested in those representations of G. So I'll say a G representation, say automorphic, if we're thinking globally, which is that is so-called H distinguished. Probably a better notation from this perspective would be to maybe call it M distinguished. And so what does this mean? Well, if F is local, this means that if I look at my representation and I restrict it to the subgroup H, then I might hope for an H invariant functional. That's the sort of thing that comes up. And globally, this is the notion of period integrals, which roughly means that if I take the integral over the automorphic quotient, I get an invariant, I get a non-vanishing integral when I take some vectors in my representation i's. These are the sorts of arithmetically interesting questions that come up in the relative Langlands program. That's sort of the point of view for where this arises. And so how is this at all related to this picture, and what is the duality here? My goal here is to sort of indicate what you should think of as M check. Well, we've for several years now had a sense for how to understand what is happening here due to the conjectures of Sakellaridis and Venkatesh. Namely that, I'll put quotes here because, again, life is somehow never as simple as we want. So when is a representation going to be H distinguished? Well, we would like to state something in terms of this parameter. So maybe, and so the statement is that phi b is M distinguished if and only if I look at this parameter coming from punctoriality, I'll just call it the Galois group just for simplicity, associated to phi. What one can do is there's actually a dual group associated to such a variety, Gx kappa or Gx hat, and in fact, there's a morphism from this dual group of this variety to the dual group of G, and in fact, it's true that there's sort of a correct way of putting a Galois action coming from the fact that X is defined over this field that we're interested in. So we have if you'd like, a notion of an L group. And we would like the parameter to factor through this. So this is actually an example of this sort of functorial lifting. So in particular, distinction should have something to do with functorial liftings, but there should be more. So I'll say, and oftentimes there's an L value. So this is where the arithmetic properties of these things become quite rich. There's some automorphic L function associated to the variety, and oftentimes that can, the statement can be phrased that the representation is distinguished if your parameter factors in this way, and there's some non-vanishing in the L function. So let me give an example that will be kind of an important guiding one for us. So the case that I think is somehow the most illuminating is due to Friedberg and Jacquet. So they take G to be GL2N and H to be this maximal Levy subgroup GLN squared. So what they prove is that, let's say, a cuspidal automorphic representation is, so here X is always going to be this quotient, is H, there's X or M, I'll say P star X distinguished if and only if its parameter up to GL2N factors through the dual group for this variety, which happens to be a symplectic group. If you look at the standard L function, the Goldman-Jacquet L function, its central L value is non-vanishing. So this is somehow like a quintessential example of this sort of a theorem. And to be really precise here, you know, where you don't actually have a notion of parameters, this can actually this factorization of parameters is actually a theorem locally, where you have local Langlands, and globally this will be stated in terms of the, let's say, exterior square L function as a whole, which is a nice way of encapsulating arithmetically that if you look at the standard representation of this group, the Galois action actually stabilizes some line. Okay.
So typical pi.
I'm sorry.
Typical pi.
Oh, I'm so sorry. Pi is a little. Kidding. Yes, sorry. Okay. So what is the point of saying all of this? The point is to motivate what they formulate as this in check in this setting. So the conjectural formulation in check, well, the actual variety itself is a little involved to write down, but it's built from essentially this sort of a data is built from two pieces of information. So namely, you take this morphism, and actually I'm hiding a somewhat important fact that often that you actually need commuting action of SL2. There's somehow some nilpotent orbit that you need to keep track of here, which is this morphism is trivial in this case, so I'm not lying there. And one more piece of data, a symplectic representation of this dual group, GX check. So in this particular case, in the example, we have the morphism SP2N mapping to GL2N, and this representation SX, we need a symplectic representation. It turns out that the correct thing to do is to take the cotangent bundle of the standard representation of the symplectic group. You might ask why we take this sort of double version, and it turns out that it actually is even visible back in the work of Friedberg and Jacquet. Namely, they write down an integral representation of these they write down these periods and they actually give a formula relating it to these L values, and what shows up is the square. So this sort of double representation is already there. Okay, so this is the sort of framework, and one of the points that will come up at the very end of the talk is that, so in this relative duality, the concept of functoriality is sort of enhanced to a notion of relative functoriality. And so the relative functoriality, where you take, say, an MH distinguished representation of H to an M distinguished representation of G. This should be related to a Lagrangian correspondence, maybe derived between the dual of this correspondence L, between these dual Hamiltonian varieties. So in particular, at the end of the talk, I'll explicitly state there exists some Lagrangian in some context, and it's the point is that this is the manifestation in this framework of relative functoriality. Okay. So now I would like to say how this connects to some things that I've thought about. But before I do, are there any questions so far?
Possible to give a quick indication of how this L function finds and how X and
Yes, so what happens is, well, okay, so this is something that's going to come up explicitly in a second. They actually formulate this, I mean, probably I'm not the right person to ask, but in terms of how they describe it in the paper is that this is identified more or less from examples. Like there's a way of understanding how you build this from the color data of the variety, but they give a conjectural formula for this representation, just built on studying tables of integrals of L functions. But the points that will come up is that this representation will come up sort of automatically in a second for symmetric varieties. And here's the problem.
so just the notion of L function depends on this syntactic representation.
Yes, that's right.
Non-linear, right?
Say again.
X is some algebraic variety.
X is some algebraic variety. Right. So this notation just means that to the variety X, there should exist some L function. You can formulate this in terms of the Plancherel density in the unramified spectrum, for example. The arithmetic problem that showed up for me was at some point here, I lost track of the fact that the Galois group was acting, which was important in the context of functoriality. And this presents a problem for me in the context of endoscopy. And so the point is that M check, even they recognize this. This isn't sort of a novel problem or novel observation, but M check does not determine the variety X G mod H up to, let's say, isomorphism. Or even, I mean, there's a looser identification in terms of up to pure inner twist. It's not determined by somehow this data. So in this context here, what we have is we have a Galois action here and here. And it's sort of obvious the problem is this representation. But this is sort of I'm saying this in a sort of an after the fact context. This was somehow not the way I was thinking about it. Just happily it ends up being the same. What's an example?
I don't understand better what you know. So are you saying like M check doesn't determine like G mod H is, so you've been calling it, T star or something.
Yes, okay.
So are you just saying uncheck, like many N's can go to the same?
That's correct, that's correct. In particular, I'll write down two examples that come up and have different arithmetic content. So let E over F be a quadratic extension. Then you could have X1, which is the variety we were just looking at. Or you could have X2, where you take a Galois twist of this. So you take the restriction of scalars E to F. DLM. So these are two varieties that are defined over, say, a local or number field. They certainly become isomorphic over a quadratic extension, but they have very different arithmetic properties. Namely, distinction for one is not. So, for example, here the distinction has to do with this standard L function squared, and here it turns out, due to a conjecture of Woe and Jacquet. This case has to do with the base change to E L function. So arithmetically, these are different. Distinction for one variety does not imply distinction for the other, and so this becomes sort of a problem that will hopefully become clear by the end of the talk in this context of endoscopy. Take it. All right. I've lost my place. No, okay, so this is actually, this example completely motivates what the problem is. I mean, the problem is that there exists an isomorphism over E. And in fact, you can do it in such a way where it acts like if you sort of act by Galois here and then take the isomorphism, act by Galois and map back, you get a nice automorphism of one variety that plays well with the larger group. But the problem here is when you do that, you actually get an outer twist of this stabilizer group. That's the exact issue. So I call these, for lack of a better term, G outer forms. Okay. All right. So the point here is that this is what came up, and there's an actually pretty easy solution. Outer forms. Let's see. Looking at time. Okay. Yes.
Are these somehow analogous to, I don't know, the real forms of the complex group?
Yes, exactly. So this is actually something that has already come up in a simpler way. When I first described endoscopy, let's put a box here, I had this stabilizer subgroup of some centralizer like this. And I said, oh, well, there's some endoscopic group H, and you want to consider the transfer. What happened here is that because this inclusion actually behaves nicely with the Galois action everywhere, this actually pins down a unique up to isomorphism quasi-split group here. So this is a well-defined group. It's either a unitary group or a linear group. There's no choice. That's the precise issue that comes up here. So we don't yet have enough Galois action to pin things down up to inner isomorphism. And we would like a sort of notion of a quasi-split form over a number field or a local field so that we can really use this notion of relative functoriality to prove some theorems. And so it's just a structural problem with spherical varieties over a field. And so it's actually quite easy to do in the end. So for the sake of time, I will sort of not say too much, but the idea goes back to a result of Losev, who computes. So let's let G mod H be just a homogeneous spherical variety. So Losev, in his study of these things, computes the automorphism group. So the G equivariant automorphisms of this sort of quotient. Once I've identified it as a quotient, this is easy to say what it is abstractly. It's just the sort of the right action on this cosets by this sort of a quotient. It's a relatively simple thing. But the critical result is that there exists, he doesn't say it this way, but this is sort of the important point. There exists a canonical quotient, which I'll call, for lack of a better term, geometric automorphisms. He refers to these as so-called distinguished automorphisms. And morally, what this quotient, this is like, abstractly, this is just a product of a bunch of mu2s. Like, this is a very small group. But what it does is this encodes the action of an automorphism on the geometric property invariance of H. So I'll say the real statement is on the Borel orbits of X. So let me give a quick example. So this is something for people who are familiar with spherical varieties. This is quite a natural thing, you might hope. This is the combinatorial aspect of this set of Borel orbits is crucial to the study of spherical varieties. But just as a quick example for what's going on here, for X is equal to GL2m mod GLN squared, this geometric automorphism group is just a single mu2, and an automorphism maps to -1 if phi swaps, or I'll say permutes non-trivially the colors of the variety. So what that means is, so in the case n is equal to 1, I just have GL2 mod a torus, GL1 squared. This actually breaks apart as an open orbit for the Borel. That's the property of being spherical, and exactly two codimension one, so two Borel stable divisors. These are the colors, and the automorphism will swap these. This one actually, like the geometric aspect of this is also, if one prefers, this acts non-trivially on the orbits in the nil cone. So these somehow records how automorphisms meet the various structure theory of these spherical varieties. Okay, so what's the point of all of this? The point is that this group is so combinatorial that there's actually somehow a canonical splitting. So we can state the following. Yeah. So let's let X be G over our field F. So we get an action of the Galois group on, for example, the F bar points. There exists a canonical one cocycle, which I'll call C sub X, from the Galois group F to this automorphism group of F bar, such that there's sort of a technical assumption that such that if X is, I'll state the word, well adapted, which, by the way, well adapted, they make some assumptions in BZSV about like the properties of the variety. So in particular, like if, for those who know the word, if this is hyperspherical, then X is well adapted. It's some constraint that is sort of hard to say too precisely. But most varieties that we're interested in are well adapted. So what's the statement then? So let's say this is well adapted. This is a geometric constraint, so I'll say it's well adapted over the algebraic closure. And X1, X2 are two F forms of this variety. Then x1 is a G outer form of x2, meaning that if I write this as G mod h1, this is G mod h2 for the same K group G, then h1 and h2 are outer forms by an inner automorphism of G, just like this example here. If and only if these are not cohomologous. So this gives us a constraint, a cohomological way of picking out such outer forms.
I think what it uses or about the assumption, so you think that there exists for every x, there exists a cycle such that what? So that if you have
1%.
well, sorry, 1%, such that if x1 start two forms which are
So they're G inner forms. So they become isomorphic in a G equivariant way over the algebraic closure.
but not isomorphic.
Not isomorphic over the ground field. Otherwise, they're cohomologous. But if they become isomorphic over the algebraic closure in a G equivariant way, so that tells you that H1 and H2 are K forms of one another. They become isomorphic over the algebraic closure, but they're going to be outer forms of one another precisely when these cocycles are not cohomologous in H1 of this automorphism.
So the way this number three, it only makes sense for homogeneous.
As stated, this is only for homogeneous varieties. That's correct. Yes. I don't know what to say more generally. Okay. Okay. So how does this connect? So this is something that's pretty general. My work on endoscopy has focused on the case where, so let's assume that X is actually a symmetric variety. So that gives us a lot more structure. Namely, there's some automorphism that enters the picture. So let's assume that it's symmetric in this sense. Then one of the things, for example, is it's easy to sort of understand how, like, the various rational forms of symmetric varieties, they're somehow more well understood. Then I'll just to be safe, I'll say if this is hyper-spherical, but that's just sort of a technical thing that we can ignore. Every example I'll give satisfies this. Then the data of this cocycle is equivalent to a symmetric or symplectic GX check representation as X. This has to do with Low-Steps computation of this is in terms of lattices, and so there's a canonical way of associating something here to a particular highest weight of this dual group. And it turns out that it always gives a symplectic, actually minuscule representation, and a compatible Galois action on this representation, so that we actually get a representation of this L version of the group. So in this example that I've erased, for this one, the cocycle, this group is just mu2. This cocycle is trivial. The Galois acts trivially here. And then this twisted case, you can probably guess what it's going to be. It's going to be the unique, the Galois action here is trivial, so you get the unique quadratic character of the Galois group that factors through E over F, and it's not the non-trivial character there. So there's sort of a natural, I mean, it's precisely what you would have hoped is true in this case. But somehow everything works canonically, so we can work completely generally. And so just to tie things back with BZSV and then try to finish with how this relates to my thinking on endoscopy. Yes.
Quick question, sorry. Just going back to part one.
Yeah.
I'm sure you said this, maybe I just was tuned out at that moment. The G outer form means can you just say again what G outer form?
Sure. That means that, so these are defined over the ground field F.
Yeah.
They become isomorphic in a G equivariant way over the algebraic closure. In such a way, so that assertion gives you an inner automorphism of G, which twists the Galois action of H1 to the Galois action of H2. So it's inner in terms of a G, but it gives you outer forms of this subgroup H.
Thank you.
And that's exactly what's happening here. This is an outer form, but it's conjugated by a normalizing element of this levy.
Beautiful. Okay, thanks.
Yeah. Okay, so the connection here is that, so this just comes out, there's this representation. But in this symmetric case, I mean, you can just check, this actually gives exactly their prediction for what this representation is. It matches precisely what they say. And so in the symmetric case, SX agrees with the formula from Ben-Zvi, Sakellaridis, Venkatesh. And in particular, it establishes that it is in fact symplectic. So the consequence is that the dual Barat Hamiltonian that they formulate is Hamiltonian and comes equipped with now a canonical action of the Galois group from the rational form. So we didn't have that action on this representation before, but now we get it. So it is Hamiltonian and has a Galois over F action. So this is sort of the problem that we were running into. So this just sort of comes out. This was not at all a consequence I was thinking of. I was just trying to understand this question, but surprisingly, once the paper came out, it's precisely the same representation.
Can you explain how CX produces a symplectic representation?
It has to do with the computation of this group. So I can talk to you about it afterwards if you'd like, but
So is it like case by case or
so the check that it is symplectic does boil down to the classification for symmetric varieties. That's absolutely true. In particular, at no point am I constructing a symplectic form somewhere. It's somehow built into the classification. That's something that, for example, is why I can only say this theorem for symmetric varieties. Okay, so I have 15 minutes and I would like to say some things about endoscopy.
So I have an assumption that if T targets are spherical, then all this so this you're using this condition like also in terms of classification or you kind of using the Kuiper's definition of Kuiper's theories.
Oh no, so this is like way more than enough. This is not implicit, like for example, I do not assume like no type in roots or anything like this for the majority there, but there's some sort of weaker constraint that I have to work with. And so I don't actually use this hypersphere. This just happens to be sufficient for this to.
You're saying so you can construct this with great generality.
Yes. Knopp and Schalke construct the dual group in much greater generality. There's a lot of problems arithmetically, but in particular, you can at least write down this dual Hamiltonian in these more general settings. I'll give an example at the very end where it doesn't fit into that framework because it has disconnected stabilizers, but endoscopic varieties are easy to write down. Right. So I don't know exactly how it fits into their framework, but my hope is that it will eventually. So endoscopy. All right, so to be quick here. Right, so now we're in a setting that we can think in terms of the Hamiltonian. So recall that what was endoscopy? We started with just a semi-simple element in the dual group, and we took its centralizer And then we dualized. Now this process is completely guided by the structure of the trace formula in terms of certain arithmetic duality theorems that give rise to these semi-simple elements, but something similar happens in the relative setting. And so what I'll say for the sake of time is that in the relative setting, so let's let M check be this dual Hamiltonian. It fibers as a vector bundle over the dual group of G modulo the dual group of X. And what's important here, this is actually going to use the fact that this is a simple, I'm using symmetric spaces. This variety actually comes equipped. Oftentimes this is this is a symmetric variety. Sometimes it's not, sometimes it's just there's a symmetric variety of a levy that's somehow induced, but oftentimes it's a symmetric variety, and from that you actually get a sort of a group valued version of the moment map an embedding, a closed embedding of this variety into G. So that's something that's peculiar, at least in the examples I've looked at, to symmetric varieties. I don't know how it generalizes, but from using this, if I take an element S in this variety, which is, say, semi-simple in the sense of geometric invariant theory, its image here gives me a semi-simple element of the group. And so I can take its centralizer. So this is some centralizer in check, this element S. But again, I'm thinking of it as semi-simple in this variety. And so because it comes as a point in this variety, which has a natural action of the dual group acting on this symmetric variety, I also get a stabilizer inside this dual group, GX, and so I get a pair, GS, and a subgroup of the, let me write down the diagram here. Diagram like this. And this uses this embedding. And so what one can hope is that there's associated to this top row, there's, we dualize, we get an endoscopic group. And so we can hope that there exists some variety, a GS variety that corresponds to this morphism here. I'll give some examples, but let me go ahead and state the theorem. So I'll give this quotient here a name. Let's call this X hat, this quotient here. This is what the notation from the paper, VZSV as well. So I'll let S be a semi-simple element of this sort of a dual variety. And to be perfectly honest, I need to take it inside some locus, which is again sort of guided by the trace formula, which semi-simple elements are correct to look at, which I could say more about, but we can just ignore this for now. So then there exists a unique up to isomorphism. And there's, to be perfectly fair, I need to, let's just keep that hyperspherical assumption. Unique up to isomorphism, symmetric GS, so this endoscopic or GS variety, X sub S, such that if I look, it induces this map, so G XS is the dual group for this endoscopic variety. And how do we pin it down in terms of this representation? The point is that the Galois actions are compatible. So if I take the symplectic representation of this larger group and I restrict it to this centralizer, there's a Galois equivariant embedding into the symplectic representation of the endoscopic variety. So that's what pins things down uniquely. And the up to isomorphic, so that would tell me that I have something unique based on the prior theorem, that this Galois action on this variety somehow pins things down up to inner isomorphism. The up to isomorphism is because for symmetric varieties, again, you can show there exists somehow a quasi-split form once you pin things down within an inner class. Okay, so this is just this is in a sense the definition. There exists a notion of what I would call an endoscopic variety. But what do you do with it? Well, so let's assume that F is a number field. So my guiding sort of goal was to formulate a notion of a stabilization of a relative trace formula. And even to try and write this down, you needed to have a notion of endoscopic variety. And so what this gives you is that, let's stick with the assumption that this is hyperspherical. Then to the variety X, there exists a distribution. This is just, let's say, the relative trace formula for X. So, you know, this is something, this is not part of my theorem, maybe we'll say elliptic, just so it's actually well defined. Otherwise, there's convergence issues. But morally, this is the distribution where instead of studying traces of representation, you study weighted traces, where by weight, we mean we're twisting by these period integrals. That's sort of the goal of these relative trace formulas. There's what is called the pre-stabilizations. So the theorem is that we can express this as a sum over elliptic endoscopic. So now I have pairs where I have an elliptic endoscopic group, which I'll call just GS to stick with the notation from this side of the board, and the endoscopic variety up to isomorphism. And then this is sort of the pre-stabilization. So now what this inner sum is, we would like to say something like what we had at the beginning, where there was some stable type distribution associated with a smaller variety. But in general, there's just sort of a, I'll say, kappa invariant distribution. So there's some twisted invariant distribution here. And so now we, so this allows us to formulate the local transfer and fundamental lemma needed to express this as a stable distribution on these smaller varieties. And so this is sort of the first critical step towards developing a notion of a stable relative trace formula. And it boils down to just asking, like, can we appropriately define this notion of endoscopic datum? Okay, so I have 5 minutes. Let me just say a few things about this.
Could I ask a question?
Yes.
Here, or do you prefer, maybe I can say.
Yeah, we can, let me just say briefly,
Say what you want.
thank you. So this is a bit, this is sort of the current status. So in special cases, the application which sort of guided the majority of this research was if we take that version we have, the case we started with, the GL2N, and we do an outer form of it. So we do a unitary version of this, where these are unitary groups. Then the conjecture due to myself, this is ongoing joint work with Xiao and Wei Zhang, relates these periods, so distinction for these periods, H distinguished, relates to the central L value of the base change L function for, now this is something that occurs in the unitary group side. And so there's a particular comparison of trace formulas that we've formulated. And this also has applications to sort of arithmetic settings where this is related to cycles on Shimura varieties.
Which base change is that?
Excuse me?
Which base change is that?
This is stable base change from the unitary group to GL over the quadratic extension used to define the unitary group. So in this case, this is some older work, and it sort of motivates this, is that in this setting, I have, so the endoscopic varieties, XS, is always of the form U2A, UA squared, just smaller ranked versions of this guy, where A plus B is equal to N. These are the only endoscopic guys which occurred, and I've proven the fundamental lemma and sort of most of the transfer conjecture. So the relevant trace formula for X is, call this A comma B, has an expression, and again, I need to put the word elliptic, A plus B, stable relative trace formula for XAB, some transferred function on these smaller groups. So this formula holds. Maybe I need to put a star here to indicate that I don't have all the terms due to convergence issues, but this is sort of already enough for some applications where this relative trace formula that we're working with that encodes this base change L functions somehow only work. Functoriality only works with stable objects, and so it compares to these terms. And so that's sort of the main application that we're working with. So I have a whole table of examples, but I'm out of time, so I'll stop here.
Thank you for this exciting talk. Are there more questions, please?
Yes.
So maybe I wanted to go back just to maybe not this theorem, but the theorem that unfortunately the race.
Oh no. Okay.
It's the one about characterizing, Sasha that's meant about characterizing the symplectic representation.
Yes.
Like, so I don't know if I'm asking a sensible question, but I'm just curious. Is there some context where like I don't know, maybe you're already over algebraically field or something like this, where where the cocycle is as trivial as possible, and you're like,
There is no, yeah, so over the algebraic closure, this is not a problem. There is no cocycle. This only appears in the arithmetic set. But for example, sorry, just to sort of illustrate this problem here. In this case specifically,
this case, like,
sorry,
yeah.
this is in the way.
It's okay. It's okay.
In this unitary case, you know, you have this problem where this again has this outer form where E over F is used to define the Hermitian form. And this is a different period that has different arithmetic properties. It's a very useful, there's kind of a lot to say here. In this case, the Galois action swaps these two term pieces of this cotangent bundle of this vector space. And so there's the sort of canonical Gx invariant polarization is not Galois stable. And whereas in this case it is. And so there are sort of arithmetic consequences that come from the existence of these things. And so like in just studying the geometry of the trace formula, there was no way a priori to distinguish between this variety versus that variety. And so but it's a pure, but once you pass to the quadratic extension, the difference evaporates. It's purely an arithmetic thing.
So, yeah, so I think I'm maybe asking about, right, I think maybe what you're saying is all of this kind of interest is before you have.
Yeah.
So maybe I'm gonna disappoint you by asking the question about once you go to the quadratic extension, but is it like, I'm just trying to understand the content. Once I go to the, I mean, are you saying that the symplectic representation at that point, I just don't understand the content.
I see. So here's
completely trivial.
Yeah, so here's
mean to then invent.
the statement then is that, so when they write down this representation, they use this framing of color of even sphere type. There's some geometric invariant, the colors of the spherical variety. And there's specific ones they isolate, that when these things, they call them colors of even sphere type. When they exist, then you can use that to construct a representation of.
So that's kind of inputted into your.
Yeah, so the sort of non-obvious thing to me was, it turns out after the fact that these are precisely the same things, or they are precisely related to what Losev identifies as distinguished roots, spherical roots.
Great, I see. So your theorem is kind of like twisting, starting from this kind of coloring and so on.
That's right.
Understand.
That's right.
Okay.
Yeah. So that's actually how the identification. It's only like after the fact, once you realize that these are like, we were just staring at the same things for different reasons.
Great.
And I will say to your earlier question, there's something it's just true that the identification with these symplectic representations goes through a case-by-case argument. It's some reduction to this simply connected absolutely simple setting, and then there's some classification, and it's just true that these things are precisely in bijection with the symplectic spherical root systems for symplectic or symmetric varieties. So it would be very nice to understand, like somehow this was sufficient for my goals, but I would, it turns out to be the same thing that they were looking at. Hey, yeah.
So I didn't quite follow the construction of this endoscopic varieties. Is it too simple-minded to say, like, if I have a Hamiltonian G-dual space, there's a functor to Hamiltonian centralized or semi-simple element space, and then I take the dual of that?
So this is sort of an ongoing. I need to. I'm not sure exactly what you said. I have a Hamiltonian.
You have a G-check space, Hamiltonian G-check space.
Yeah.
Now I want to get a Hamiltonian G-check of S space,
Yes.
right? Right, it's a bimodule.
That's right.
With restriction, and then just take the dual to that as a Hamiltonian H, or whatever, the endoscopic group space, right? I mean, there's a duality on Hamiltonian spaces for the endoscopic group.
Mm-hmm.
So is that what the space is? I guess, is it just the dual to kind of restriction of the?
You're saying just restrict this to the subgroup? Or like, I'm not exactly.
Yeah, I don't know, but
I don't know exactly what. Somehow I don't know a priori what this bimodule is here.
well, there's a restriction. There's a
The restriction. It's not the restriction map. Right. In some sense, right. So I like in particular, it is true. The only way I know to see that is in special cases where the MX has is polarized. But for example, in the case where GL2N plus 1, GLN plus 1, somehow this is not obvious a priori something kind of nice happens here. I don't know how to. I mean, maybe we can discuss that. I don't know how to see it more generally.
Can I try to re-ask his question? Maybe I don't. So like if we go back to your theorem.
Yeah.
So you construct, your theorem constructs this XX. I don't know if I'm supposed to say to fit into the context of David's question, maybe I'm supposed to say T star XS or something like this. So if you take T star XS.
Yeah.
And take it dual, I mean, go, so it's kind of some.
Right.
Some, and I don't know what letters to use, I don't want to bias us toward.
No, it's
Does it
okay,
have
it's
some
okay.
Obvious, I don't know, obvious, does it have some geometric relationship?
Yeah, no, so this is, I mean, this is something, it would be very nice to know how to see this a priori.
Like for Bruce, right, I mean, it is just.
So in certain cases, you know, in this, at the very end of the paper, I just make the observation that there actually exists a Lagrangian correspondence between these. I don't know how to do it in general. So that's, I mean, maybe the answer is that, I suspect the answer is yes, I just didn't quite see how to.
But it's not something often.
So Lagrangian corresponds between the restriction of one. Hamiltonian which-
Yeah, yes, that's right. So, I mean, that's right. You sort of, I mean, just as an example, like, let's just look at the example of this case. So you have T star, GL 2N mod SP 2N C2N cross. So this is the dual Hamiltonian for this case. And so this projection GL2N C2N. Embedded in this is GL2A SP just as an orbit. 2B SP 2B. And it is true that the appropriate cotangent bundle where, you know, you just fiber this, or you break it, that is exactly true. And so you can use this embedding here to get pull back and then project, and that gives you a Lagrangian correspondence in this case. Doing the exact same thing where I replace 2n with 2n plus 1, it's sort of non-obvious that it works, but it does, because that's somehow a non-reduced thing. So, but I would love to maybe. This was something I noticed after the fact, so it would be very nice to understand what's maybe a more canonical way of saying this.
Well, I think we'll